Welcome back. Last episode, we wrestled with improper integrals, infinite intervals, convergence tests, the p-integral table. Today, we step back into clean geometry and answer a simple question. Given two curves, what's the area of the region between them? The setup is exactly what it sounds like. Two functions f and g, defined on some interval from a to b, with f on top and g below, meaning f of x greater than or equal to g of x everywhere on the interval, they sandwich a region. We want its area. The formula is one line. The area equals the integral from a to b of f of x minus g of x. Replace the integrand with the vertical gap between the two curves and integrate. That's it. Today, we'll derive that formula from the Riemann picture so it feels inevitable, find the bounds by intersecting the curves, handle the case where the curves swap which one is on top, and learn a useful trick. When the picture is more naturally horizontal, integrate in y instead of x. 3 worked examples to lock it in. Let's go. Let me say this carefully. We have two functions, f and g, both defined on a closed interval from a to b. The hypothesis is that f is the upper curve and g is the lower curve, f of x greater than or equal to g of x for every x in the interval from a to b. The region R between them is the set of points x, y with x in the interval from a to b and y between g of x and f of x. Geometrically, it's the region you'd shade with a pencil if I drew the two curves and asked you to fill in the space between them. The vertical strip at horizontal position x, a thin vertical sliver of the region, runs from y equals g of x at the bottom up to y equals f of x at the top. Its height is f of x minus g of x. Its width, when we make it infinitesimally thin, is dx. So its area is the quantity f of x minus g of x times dx. Sum up all the strips by integrating from a to b. The area is the integral from a to b of the quantity f of x minus g of x dx. That's the formula, in one line, derived informally but pictorially. The key conceptual point, the integrand, is the height of a vertical strip at position x. Every area between curves problem reduces to identifying that height and integrating it. Let me give the Riemann derivation, because that's where the formula becomes obvious. Partition the interval from a to b into n subintervals, each of width delta x equals the quantity b minus a over n. In each subinterval, pick a sample point x sub I. We're going to approximate the region by a bunch of vertical rectangles, one per subinterval, just like episode 2. But there's a twist. Each rectangle now stretches from the lower curve to the upper curve. At sample point x sub I, the rectangle has width delta x and height f of x sub I minus g of x sub I, the vertical distance between the curves at that x value. Its area is that height times that width. Sum across all n rectangles. You get the sum of the quantity f of x sub I minus g of x sub I times delta x. That's a Riemann sum, not for f alone, not for g alone, but for the difference f minus g. Passed to the limit as n approaches infinity, the rectangles get thinner and thinner, the sum converges to the integral from a to b of the quantity f minus g dx, the Riemann sum converges to the Riemann integral, and the integrand is whatever the rectangle height is. That's the whole derivation. We didn't invent a new kind of integral. We used the integral we already had with a smarter integrand. The clever part is recognizing that the right integrand is the gap, not either function alone. In most textbook problems and most real problems, you aren't handed an interval from a to b. You're handed two curves and asked for the area of the region they enclose. The interval is whatever interval the two curves cut out on their own. To find it, you intersect the curves. Solve f of x equals g of x. The solutions are the x values where the two curves meet, the corners of the region. If the curves intersect at exactly 2 points, those two x values are your a and b. Example, the one will work in full in a moment. Take f of x equals x, a straight line through the origin with slope 1, and g of x equals x squared, a parabola. Set them equal, x equals x squared, rearrange to x squared minus x equals 0, factor to x times the quantity x minus 1 equals 0. Solutions, x equals 0 and x equals 1. So the line and the parabola cross at the origin and at the point 1, 1. Between these two crossings, on the interval from 0 to 1, they enclose a little lens-shaped region. That's the region whose area we want, and the bounds of the integral are the x-coordinates of the intersections, a equals 0, b equals 1. The bounds are determined by the geometry, not given to you. And before you integrate, you need to figure out which curve is on top, so you put it first in f minus g. On the open interval from 0 to 1, plug in x equals 1/2, f of 1/2 equals 1/2, and g of 1/2 equals 1/4, so f greater than or equal to g there, meaning the line y equals x is above the parabola y equals x squared on the open interval from 0 to 1. Set up the integral from 0 to 1 of the quantity x minus x squared dx. First worked example, the classic. Area between the line y equals x and the parabola equals x squared. Intersections, x equals x squared implies x equals 0, 1, as we just found. Top curve on the open interval from 0 to 1, the line y equals x is above the parabola y equals x squared. Quick check, at x equals 1/2, line gives 1/2, parabola gives 1/4, line wins. Set up the integral from 0 to 1 of the quantity x minus x squared dx. The antiderivative of x is x squared over 2. The antiderivative of x squared is x cubed over 3, so the antiderivative of x minus x squared is x squared over 2 minus x cubed over 3. Evaluate from 0 to 1. At 1, 1/2 minus 1/3. At 0, 0. Subtract 1/2 minus 1/3 equals 3/6 minus 2/6 equals 1/6. The area is 1/6. 1/6 of a square unit. The region is a tiny lens shape inside the unit square from 0 to 1 by 0 to 1, and it occupies 1/6 of the unit square's area, plausible just from looking at the picture. Memorize this answer, 1/6. The number 1/6 shows up across calculus surprisingly often, and the area between line and parabola picture is its most famous source. Here's a wrinkle. What if the two curves cross somewhere inside the interval, not just at the endpoints? Then on one side of the crossing, f is on top, on the other side, g is on top. The expression f of x minus g of x changes sign. If you just plug into the integral from a to b of the quantity f minus g dx, without thinking, the integral computes signed area. Positive contributions from where f is greater than or equal to g, and negative contributions from where g is greater than or equal to f. They can partially cancel, and you don't get the geometric area of the region. To fix, use the absolute value of f minus g as the integrand. The integral from a to b of the absolute value of f minus g dx gives the true geometric area. In practice, you don't deal with the absolute value symbolically. You split the integral at every crossing. If f and g cross at c in the open interval from a to b, you split into two pieces, from a to c and from c to b. In each piece, you figure out which curve is on top, right top minus bottom, integrate, and sum the absolute values. So the procedure is, find all intersection points in the interval from a to b, not just the endpoints. In each subinterval between consecutive crossings, identify the top curve by plugging in a test point. Integrate top minus bottom on each subinterval. Add up the pieces. Geometric area is always positive. Signed area can be negative or partially cancelled. We want geometric area, so we handle signs piece by piece. This is the one thing students forget. Second example. Area between y equals sine of x and y equals cosine of x on the interval from 0 to pi over 4. Top curve at x equals 0, sine of x equals 0, and cosine of x equals 1. Cosine is on top. Sine grows, cosine shrinks, and they meet at x equals pi over 4, where both equal the square root of 2 over 2. So on the whole interval from 0 to pi over 4, cosine of x is greater than or equal to sine of x, with equality only at the right endpoint. No internal crossing. The curves meet exactly at the endpoint of our interval. Set up the integral from 0 to pi over 4 of the quantity cosine of x minus sine of x dx. The antiderivative of cosine of x is sine of x. The antiderivative of negative sine of x is positive cosine of x. So the antiderivative of cosine of x minus sine of x is sine of x plus cosine of x. Mind that sign, the negative sign flips to a positive cosine. Evaluate at the endpoints. At pi over 4, sine of pi over 4 plus cosine of pi over 4 equals the square root of 2 over 2 plus the square root of 2 over 2 over 2 equals the square root of 2. At 0, sine of 0 plus cosine of 0 equals 0 plus 1, subtract the square root of 2 minus 1. The area is the square root of 2 minus 1, roughly 0.414. A small crescent-shaped sliver between the two trig curves pinched off at the intersection point x equals pi over 4. Notice this answer also has a clean closed form, even though it involves the square root of 2. Almost every textbook area between curves problem comes out to something tidy. 1/6, the square root of 2 minus 1, 9/2. It's the nature of polynomial and trig curves giving polynomial and trig antiderivatives. Here's a useful trick. Sometimes, instead of integrating in x, you should integrate in y. The motivation, occasionally the two curves bounding your region aren't conveniently functions of x. The classic case is a sideways parabola like x equals y squared paired with a line x equals y plus 2. If you try to express the parabola as y equals something in x, you get y equals plus or minus the square root of x. Two branches, you'd have to split, it's a mess. But x equals y squared is a perfectly clean function of y, and x equals y plus 2 is 2. The picture is naturally a function of y, with x on the horizontal axis as output and y on the vertical axis as input. The fix is to switch how we slice. Instead of vertical strips of width dx, use horizontal strips of height dy. At a given height, y, the horizontal strip runs from a leftmost x value, x sub L of y, to a rightmost x value, x sub R of y. Its width is x sub R of y minus x sub L of y. its thickness is dy. Total area, integrate the quantity x sub r minus x sub l in y from y equals c at the bottom of the region to y equals d at the top. Area equals the integral from c to d of the quantity x sub r of y minus x sub l of y dy. Same Riemann picture, rotated 90 degrees. It's the same formula structurally, right minus left and y instead of top minus bottom in x. Choose whichever variable makes the region easier to describe. Third example, the payoff of integrating in y. We have a parabola y squared equals x, a parabola that opens to the right with vertex at the origin, and a line y equals x minus 2, a line of slope 1 crossing the x-axis at the point 2, 0, and the y-axis at the point 0, negative 2. They cross in two places, enclosing a lens-shaped region. Rewrite both as functions of y, x equals y squared for the parabola, x equals y plus 2 for the line. Find intersections by setting the x values equal, y squared equals y plus 2, rearranged to y squared minus y minus 2 equals 0. This factors as the quantity y minus 2 times the quantity y plus 1 equals 0. So the intersections are y equals -1 and y equals 2. These are the bottom and top of our region in the y direction. Which curve is on the right? Pick a test point in the middle, say y equals 0. Line gives x equals 0 plus 2 equals 2. Parabola gives x equals 0 squared equals 0. Line is to the right. So x sub r equals y plus 2, the line, and x sub l equals y squared, the parabola. Set up the integral from y equals -1 to y equals 2 of the quantity y plus 2 minus y squared in dy. Antiderivative y squared over 2 plus 2 y minus y cubed over 3. Now we evaluate at y equals 2 and at y equals -1 and subtract. Now we evaluate. The antiderivative is f of y equals y squared over 2 plus 2y minus y cubed over 3. Plug in y equals 2, 4 over 2 is 2, plus 2 times 2 equals 4. Minus 2 cubed over 3 equals 8 over 3. Total, 2 plus 4 minus 8 over 3 equals 6 minus 8 over 3 equals 18 over 3 minus 8 over 3 equals 10 over 3. Plug in y equals -1, -1 squared over 2 equals 1/2, plus 2 times -1 equals -2. Minus -1 cubed over 3 equals -1/3 equals +1/3. Total, 1/2 minus 2 plus 1/3. Common denominator, 6, 3 over 6, minus 12 over 6, plus 2 over 6 equals -7 over 6. Subtract f of 2 minus f of -1 equals 10 over 3 minus -7 over 6, which equals 10 over 3 plus 7 over 6. Common denominator 6, 20 over 6 plus 7 over 6 equals 27 over 6 equals 9/2. The area is 9/2, 4.5 square units, a surprisingly large region. It's the lens between the sideways parabola and the diagonal line, and stretching from y equals -1 up to y equals 2, with the line cutting across diagonally to the right of the parabola. Quick aside, try doing this problem in x instead of y. You'd split the region at x equals 1, where the parabola's two branches meet the line. From x equals 0 to x equals 1, the upper boundary is the upper branch of the parabola y equals positive, the square root of x, and the lower boundary is the lower branch y equals negative, the square root of x. From x equals 1 to x equals 4, the upper boundary is still y equals positive, the square root of x, but the lower boundary becomes the line y equals x minus 2. Two integrals, two cases, square roots everywhere. Integrating in y, one integral, polynomial, clean. That's the lesson. Choose your integration variable to match the geometry. If the picture is sideways, integrate in y. One more conceptual point, because it trips students up. The Riemann integral, the integral from a to b of f of x dx, doesn't compute geometric area in general. It computes signed area. Area above the x-axis counted positive, area below counted negative. Famous example, the integral from 0 to 2 pi of sine of x dx equals 0. The sine curve from 0 to 2 pi encloses a positive hump and a negative hump of equal size, and they cancel. Signed area 0. Geometric area is definitely not 0. It's 4 two humps of area 2 each. The same issue arises for area between curves. The integral from a to b of the quantity f minus g dx computes signed area with respect to the difference f minus g. If f stays above g on the whole interval, signed and geometric agree. But if f and g cross, the signed integral cancels positive and negative regions, and you don't get the true area between them. The fix, again, is the absolute value of f minus g. The geometric area is the integral from a to b of the absolute value of f minus g dx. In practice, split at every intersection, write top minus bottom on each subinterval, making sure that expression is positive, and sum. That's the safe procedure. If the curves only cross at the endpoints of your interval, no internal crossings, you can skip the splitting, otherwise do the splitting. Let me zoom out. There's a single template that controls all of this, and it's worth pausing on. In episode 3, we wrote area under a curve as the integral from a to b of f of x dx. That's really area between the curve y equals f of x and the curve y equals 0, the x-axis. The integrand f of x is the height of a vertical strip from the x-axis up to the curve. Today we generalized, area between y equals f of x and y equals g of x is the integral from a to b of the quantity f minus g dx. The integrand is the strip height between the two curves. The slogan, the integrand, is the height of the strip at position x. Area under f is the special case where the lower curve is the x-axis, and this template will keep paying. Next episode, we compute volumes by slicing a 3D region with parallel planes. The cross-sectional shape at position x has some area, a of x, and the volume is the integral from a to b of a of x dx. Same template, measure of the slice at position x integrated. The conceptual jump is recognizing that measure of the slice is whatever quantity is geometrically natural, a length for areas, an area for volumes, and later an arc-length differential for surface areas. The integrand always tells you the answer to what's the infinitesimal contribution at position x. One pattern infinitely reused. That's calculus. 5 common pitfalls since this topic looks easy and bites students in predictable ways. 1. Forgetting to find intersection points. In most problems, you're not handed an interval from a to bt. You have to find a and b by solving f of x equals g of x. If your final answer doesn't have a and b coming out naturally from the geometry, you probably skipped that step. 2. Wrong order in f minus g. The formula is top minus bottom, and getting them backwards gives a negative answer. The fix is trivial. Plug a test point into the interior of the interval, see which curve is bigger, put that one first. If you get a negative answer at the end, you know you had them backwards. Just flip the sign and move on, but don't write a negative area on your paper. Areas are positive. 3. Internal crossings ignored. The curves might cross inside the interval, not just at the endpoints. Find all solutions of f equals g in the interval, and if any are interior, split the integral at those points and handle each subinterval separately. 4. Wrong variable. If the regions bounding curves are naturally functions of y, sideways parabolas, circles, regions with vertical tangents, integrate in y, not in x. Save yourself the case, splits. 5. Algebra at endpoints. Especially with the cube term y cubed over 3 at negative y values, sign errors are common. Be deliberate when plugging in negative numbers raised to odd powers. The single best preventative habit, sketch the region. Even a rough sketch tells you the intersections, the top curve, and whether to integrate in x or y. 2 minutes of sketching saves 5 minutes of confusion. Recap. Setup. Two curves f and g on the interval from a to b with f above g. Area between them is the integral from a to b of the quantity f of x minus g of x dx. Derivation. Slice the region with vertical strips of width dx and height f minus g. Sum passed to the limit. Riemann's machinery applied with a smarter integrand. Bounds. Usually not given. Find them by solving f of x equals g of x. The intersection x values are the corners of the region. Crossings. If f and g cross inside the interval, split at each crossing and use the absolute value of f minus g, equivalently top minus bottom on each subinterval. Geometric area is positive. Sign handling is your job. Sideways. When the curves are more naturally functions of y, use horizontal strips. Area equals the integral from c to d of the quantity x sub r of y minus x sub L of y dy. Same Riemann picture rotated 90 degrees. 3 results to lock in, line and parabola enclose area 1/6. Sine and cosine on the interval from 0 to pi over 4 enclose the square root of 2 minus 1. Parabola x equals y squared and line x equals y plus 2 enclose 9/2. And the bigger pattern, the integrand, is the infinitesimal contribution at position x, a length for areas, an area for volumes, an arc length for surface areas. Same template, different geometric quantity. Next episode, we spin a region around an axis to make a 3D solid and ask for its volume. The integrand will be the cross-sectional area of the solid at position x, and the formula will look eerily familiar. Volumes by disks, washers, and shells. See you there. That's area between curves. If this helped, hit like, drop a comment, and consider subscribing. It's the single most useful thing for the channel. Post your favorite area, between curves problem below. Bonus points if the answer is a tidy fraction or involves a famous constant. Next episode, volumes by disks, washers, and shells. We spin today's regions around an axis to sweep out 3D solids, and the integrand jumps from length to area. Same template, one dimension up. See you there. Area between curves is the bridge topic. It uses everything we built, the Riemann sum, the fundamental theorem, the basic antiderivatives, and adds a single geometric insight. The integrand is whatever you're measuring per unit dx, and when the region sits between two graphs, that measurement is the gap. Same template will power the next 3 episodes. take the same region we computed today, spin it around the x-axis, and ask for the volume of the three-dimensional solid it sweeps out. The integrand changes from f minus g a length to pi of f squared minus g squared, an area of a washer, but the structure of the formula is identical, cross-sectional measure times dx integrated over the interval. Volumes by disks, washers, and shells. That's next time. Subscribe so you don't miss it. If you got something out of this, please like the video, drop a comment with what clicked for you or what didn't, and subscribe for more educational videos. Every like, comment, and share helps push this work to more learners, which is what this channel is really about. Thanks for watching. See you in the next one.